So welcome back. This is the first in a series I've wanted to do for a very long time, never got around to it. And the purpose of this series is to, as the title implies, debunk some common computer myths. And if you've been around the computer tech world on the internet for any amount of time, you may have seen some continuing and often repeated and amplified myths regarding computer technology that is just, honestly, some of it is just such nonsense. And, you know, it's kind of understandable that people don't understand computers because, you know, as anybody who's worked with hardware and software for any amount of time, it's clear that these are really, really complicated things because it's not only hardware, but it's software. And the software generally has a really big impact on the performance of your computer. And if you don't understand the software side and just understand or think you understand the hardware side, then you really are not sure what's going on. And I think a lot of people tend to focus on, you know, looking at hardware, and they get attracted to the hardware because it's, you know, something you can pick up and hold in your hand. It's got flashing lights, and you can look at some specs and make believe you understand it. But they're totally missing out on not only the software side that has a huge impact, and like most software is generally proprietary, so it's unknowable what the software does and how it actually affects your computer performance. So people tend to get off on these sidetracked things that are oversimplifications of things that are kind of unknowable and understandably very difficult to comprehend, but they keep repeating this stuff and they get it in their mind that it's a simple thing, and they don't understand the whole world of stuff out there that they don't even know exists. So, you know, they tend to get involved in these small issues and expand them into big things and think that covers everything. So the goal here is to try and chip away at some of those myths and provide some data behind the myths to show why they're, in general, not really true for most people. Now, again, people like to say, you know, this is true in 1% of the cases, therefore it applies everywhere. No, that's not how it works. Different people have different systems and different needs, and what applies to you or what you think applies to you may be totally irrelevant to the rest of the world. So we're going to try and chip away at some stuff, and we're going to start out with power supplies. And power supplies are kind of the front end of the computer, and it's a great area for myths and misunderstandings because really a power supply is a black box, and few people have actually looked inside the power supply to see what's in there, and much less do they understand what's in there, even if they did. And that's kind of a good thing because you don't want people opening up power supplies. From an engineering perspective, power supplies have components in there that can really hurt you and kill you. They have what are called capacitors, which can hold a charge, electrical charge. And if you touch them, you can get a major shock and it can hurt you very badly. So by all means, anything we discuss here today, by the way, about electricity and power supplies and computers, in no way am I encouraging you to touch any of the electrical components or open up your computer house circuitry and your components and your breaker panels and none of that. Don't touch any of that. Leave it to a licensed electrician. This is just for information and kind of a springboard for you to learn more things, but you really need to understand the risks of this stuff because it can be very dangerous. So please don't touch any electrical components, and don't let this encourage you to do that. You know, learn the risks and get a licensed electrician if you want to do any work on your electrical system. So anyway, that being said, we're going to look at power supplies. And power supplies are one thing for the reason I mentioned that you can't really open them up and look at them. But I think at a lower level, people don't really understand what power is. I think they have kind of a general concept, but I think electrical stuff people have never really looked at. A lot of people haven't really looked at what electricity is and what it all means. So we're going to try and step through a fairly user-friendly conceptual view using some visuals and some real-world concepts and try and figure out what really is power and what do power supplies do so that we can understand most of the myths that surround them and why in the real world they don't really apply very much. So power supply, you can see there's one in the right-hand corner there. That's an older power supply. It's one I took from an old machine. Okay, so let's take a look at what power is. And we're going to use an example in the real world of a physical system. And we're going to use this racing car here. Now, I think we generally have an intuitive idea of what power means. Power means if you've got a powerful person, they can pick something up and toss it across the room, no problem. They can accelerate it and throw things around. That's what power is. And in terms of this racing car, we know that it's got a big, powerful engine, right? And the engine is generally rated in horsepower. So there's that word power. Now, what does the engine horsepower mean? Well, intuitively, we know that if I get into this car and I start it up and put it into drive and slam my foot down on the pedal, that car is going to accelerate very quickly because the power generated by this engine is going to inject a lot of force and energy into this car and turn the wheels and get it moving very quickly. So it can move things very quickly, even if they're very heavy. Now, if I took a 5 horsepower lawnmower engine and pulled out the 500 horsepower engine, put in a 5 horsepower engine, and did the same thing, the car would just kind of look at you and not go anywhere because it's low horsepower. It can't inject energy and force into the car because it doesn't have enough power. So we can see intuitively that power is an indication of, on a real-time basis, how much energy can be injected or transferred into an object. All right, so that's power. Now, let's take a look at something that's kind of related, and that is energy. So what is energy? Well, let's say in our last example, we get in the car, we sit down, we turn on the car engine, and we put it in drive, and we slam the gas pedal. If you measure the power going from the engine to the car wheels to accelerate it, over time it will look like this. And let's say our goal is to get up to 100 miles an hour as fast as we can. So we slam the gas pedal, and you can see the power goes from 0 power. The engine starts up, we slam the gas pedal, and very quickly it goes up to maximum power. You've got the pedal to the metal, and it is injecting 500 horsepower into that car and causing it to accelerate very fast. So the pedal's down as far as you can, and you get up to this point, and you're up to your goal of 100 miles an hour. And then what you do is you let off the gas pedal because you don't need as much power to keep the car running. You needed a lot of power to accelerate it because you're moving that mass from 0 to 100 miles an hour. But now at 100 miles an hour, you can let off the gas pedal and you don't need as much power to keep it at 100 miles an hour. So you let off the pedal and the power going from the engine to the car drops until it flattens out and you're going 100 miles an hour, okay? So power versus time varies. Any point in time, you've got a different amount of power going from the engine into the car. Now, what is energy? Well, energy is a measure of the total amount of power you've injected into that car over a period of time. So you could basically look at from time 0 up to this point where you're going 100 miles an hour, say it's a couple minutes later. If you add up all of the power injected over this period of time and add it all up, that's the total amount of energy injected into the car to get it from 0 to 100 miles an hour after this point in time. So power is like an instantaneous injection of force and energy into the car in this case. And energy is a measure of the total power you've injected over a period of time. Okay? So similar but different concepts. And we're going to need to know power and energy when we're talking, of course, about a power supply. So we're also going to take a look at another analogy to bring this closer to basic electricity concepts. And we're going to use a water hose. All right, so we've got 3 examples of a water hose. On the far left, we've got a little garden hose, and you can see we've got not a lot of pressure and not a lot of water flow, right? There's very little water coming out. I mean, if you're going to fill this big tank with water at this rate, it would take, a day to fill it because there's very little water flow and it's coming out at very low pressure, right? So you've got low flow, how much gallons per minute, and low pressure, all right? Now you go to this next one, we've got the same type of water hose, and you've got high pressure. But if you think about it, the flow is probably about the same as this, but the way you've got the high pressure is you have blocked off most of the flow, so all of the whatever pressure you've got in here is pushing up against this little tiny area and increasing the pressure, so now you're shooting out the water at high pressure, but it's a very low flow. The gallons per minute to fill up this tank is very low. It's still going to take a long time to fill up the tank, but you've got a high pressure pushing it, okay? So here you've got a low pressure, low flow, high pressure, low flow, and here's the far other end of the spectrum. Here's a guy with a fire hose, and you can see right away this is high pressure, high flow. Very high pressure and a lot of gallons per minute. You could fill this tank in about 5 seconds, right, with this type of flow. Now, in terms of force and power, imagine placing your hand in front of this, all right? Low pressure, low flow, you're not really going to feel much. It's a little trickle. Put your hand in front of this and high pressure, low flow, you're going to feel a sting on your hand. So it's more power coming out, more force, but it's in no way close to this guy, right? You put your hand in front of this guy and it'll rip your arm off, right? Because you have very high pressure, very high flow, and that combines to give a lot of force. You've got this heavy weight of water being pushed at a high pressure. You multiply those two together, gives you a huge force, a lot of energy coming out of this, right? So to give you another indication, we could use our racing car. And let's say our racing car is sitting in front of this hose. We aim this hose at the racing car, and we put the racing car in neutral, and just point this fire hose at the racing car. What's going to happen to the racing car? Well, there's enough horsepower in this flow, a combination of pressure and flow, to cause that car to actually move. It's like putting an engine in the car. A 100 horsepower engine in the car, this flow is enough to actually move that car. And how far you move it and how much force you apply for how much time tells you how much total energy you've injected to the car. It's no different from the engine, right? That's a source of power that you're applying to the car, but in this case you're using water, right? So the power applied is a function of not only the of the pressure, but the flow. And we're going to see that those are very similar to voltage and current in the electrical terms, all right? So we've got low water pressure, low flow means low power. High water pressure, low flow rate means a little bit higher power. High water pressure, high flow rate means incredibly high power, enough to move a car, all right? So the analogy between water and electricity is very close. With water pressure is analogous to what's called in electricity voltage, all right? The problem with electricity is you can't see the water flowing. It's inside the wires. It's called electrons, little invisible particles moving, but the pressure that is pushing them is called voltage. And it's just like water pressure, right? But it's pushing invisible particles. And the voltage is measured in volts, all right? The rate of flow of water coming out of the hoses is analogous to the current, or the amount of particles flowing, electrical particles flowing every second, and that's called current, and it's measured in amps, all right? So voltage and current are like water pressure and water rate of flow. Same thing, but it's invisible particles, all right? Now, again, the rate of energy being delivered, either from the engine to the car or the high-pressure fire hose to the car, is the same as electrical power. So it's power, but it's electrical power. And it's measured by watts, which is voltage times current. Just like the water pressure times the current flow determines how much power is being generated by the fire hose, watts or electrical power is voltage or pressure times amps or current, right? Same concept, right? So that's what power is. It's the voltage times the current in the circuit. And then the total energy that we measured with the car, the total energy is the power over a period of time, the power injected over a period of time. It's the same with electricity. It's the watts or power injected over a period of time, and it's typically measured in watt hours or watts times hours, okay? So these are the basic concepts of electricity. Again, it's a little bit difficult with electricity because it's invisible, but if you can imagine that there's water flowing inside the electrical wires and they're going by these concepts, it should be a little bit easier. So let's look at your house and let's see how the electrical service is laid out, because it's going to be very important in understanding exactly what's going on with your computer and your power supply and your electricity, okay? So I've got here your house, and I've got a electrical utility pole outside. And coming from the pole is a couple wires that come across your yard and come to the outside wall of your house or your apartment. And the wires go through the wall and they connect to what's called a circuit breaker box or breaker panel, all right? And the purpose of the panel is twofold. One is it's going to take this single source of electricity and divide it up to different parts of your house, right? So you might have one circuit or wires that go from this panel go out to your kitchen, and they might feed a microwave and a refrigerator. And another set of wires might go from the panel and run over to maybe your office, your room, where you've got a window air conditioner and your computer plugged in. And you might have another one that goes downstairs to feed the clothes washer and maybe the heater and whatever's downstairs. And you might have another one that goes to feed some other rooms. But this is the basic concept, right? You've got a breaker panel that distributes the electricity via circuits or wires that go to different parts of your house. And these little boxes are very important. They are protective devices called circuit breakers. And what's the purpose of the circuit breaker? It is to protect this circuit and to protect this circuit. If something goes wrong, their job is to sense something going wrong and automatically, without you doing anything, open up that circuit to disconnect the electricity from that circuit, thereby leaving this other circuit working fine, still connected to the outside supply. So these things are very important. They protect your circuits and your devices. Like if this microwave was doing something goofy, then this thing would automatically detect it and hopefully open up and disconnect it and tell you, hey, you got something wrong, and you could find out maybe there's a short circuit or something. So that's the basic layout of how your electricity is in your house. Again, never go touch your electrical circuits. They are very dangerous. Now, what are you getting from the electric company? Well, most states, and I'm talking about the US, and it's probably the same in other countries, are required to provide voltage to your service. In the US, it's generally around 120 volts, all right? That is the typical range of voltage. And each state in the US generally has requirements that say that under normal conditions, that voltage can't vary more than maybe plus or minus 5 or 10%, right? So on the high end, it might be a maximum of 132 volts or 108, whatever plus or minus 10% is. So they are required under normal conditions to maintain usually plus or minus 5%, it may be 10% depending. But usually you can rely on the voltage. If you measure the voltage on any of your circuits, it's usually around 120 volts. It might bounce up and down, but under normal conditions at the utility, it's 120 volts. Now, that being said, stuff can happen under abnormal conditions in the utility. You can get a storm, or you can get, a car hitting a pole and causing problems, and suddenly you'll go to zero, right? Those are abnormal conditions, and whatever happens, happens. But generally, under normal conditions, you can assume it's probably 120 volts. All right. So, also, one other thing we know is that for most circuits in your house, if they're not very, very old circuits, and you can look at your panel if you are qualified to look at electrical panels only. Don't do it if you're not. You can look at your circuit breakers and see that they're generally rated around 15 amps. Of course, some circuits that serve big loads in your house are going to be higher, but and the main circuit breakers are going to be higher. But in general, the circuits are going to be rated maximum 15 amps, which means the flow of current, the invisible electrical flow of water in your electrical circuits, if it gets above 15 amps, these circuit breakers on either circuit, this circuit breaker will open up automatically and turn off the electricity to the circuit. All right? So that tells us if it's going to be 120 volts under normal conditions, and this thing is going to be okay until you get 15 amps, you can figure out how many watts this circuit can handle, right? Because it's 120 volts times 15 amps, and if you multiply that out, you can see that your circuit is probably good for about 1,800 watts or 1.8 kilowatts, all right? So that's good to know, because if you're going to attach your computer, you need to know whether your circuit can handle your computer, all right? So let's look at some of the other equipment that's tied on to your house wiring and see what it draws for power. Well, if you look at your microwave you look on your microwave on the specifications, on the sticker on the back, it says it's probably around 1,200 watts. Now, just because it says it's 1,200 watts doesn't mean anytime you plug it in or turn it on, it's going to draw 1,200 watts. That's very important. It's not all or nothing, right? And people tend to get to, oh, I turn it on or I plug it in and it's drawing 1,200. No, it depends on whether you've set it on high. It could draw as much as 1,200 watts, okay? Your air conditioner, depending on the type, if it's a window air conditioner, or if it's a big central air conditioner, it might be 1,200 watts like your microwave, or it might be a lot more, all right? Your computer generally is going to be around 50 to 400 watts, all right? Much less than the microwave, much less than the air conditioner, probably less than some of the other components that are drawing current, right? 50 to 400 watts. And again, 400 watts, as we'll see, is really high for most computers. I've got a computer that has 2 high-end GPUs, and only if they're running at maximum will my entire computer system draw 400 watts. It's very rare, and everything has to be running at maximum. And these are GPUs that are rated at 250 watts, one of them, and the other one is 150, which is 250 plus 150 is 400 watts. Plus my other computer components like the CPU and the motherboard are drawing power. So even that they're at their rated 250 and 150, they're not drawing all that power. It's 400 total with my motherboard and my CPU and everything else. So, it's not running at rated power, even though it technically should be. And that depends on the software, how the software, whether it's optimized for these GPUs and it's using all the cores and all that kind of stuff. And we'll talk about that later. So this stuff varies, but here's kind of a ballpark of where you can expect everything to lie. Now, what I have for my main computer is I have a watt meter. And you can see here, under normal conditions, like right now when I'm running my computer doing this work, it's running at 80 watts. And here's 78.2 watts. Normally it's about 80 watts when I'm just doing normal work. Not rendering anything, not really using the GPUs, but 80 watts doing normal work, all right? That's just typical for me, and I suspect for most people, it's probably 50 to 100 watts under normal conditions. Again, not running video games and not running video decoding and that kind of stuff, but just running a computer, doing internet and doing stuff like I'm doing right now, which is recording a video. Now, keep in mind also that a regular light bulb is going to be between 40 and 100 watts, maybe less than 40. Some of the newer light bulbs might be less, but generally 40 to 100 watts. The older light bulbs are 100 watts if you've got the old incandescents. So that gives you kind of a view that your computer may be running about the same as a light bulb under normal conditions, right? So there's no real paranoia there. It's kind of like a light bulb, right? So here's some typical maximum component requirements for the components in your computer, your desktop. Again, CPU is 50 to 100 watts. Okay, yours may vary, but in this kind of a good ballpark. GPU might be 50 to 250 watts. Even the newer NVIDIA RTX cards are a maximum of around 250, maybe a little bit more. Fans are pretty much negligible. Memory is pretty much negligible. Motherboard might be 25 to 50 watts. So again, it's tough to get 250 plus 100, that's 350. Again, you're up to 400 watts. So to keep in mind, like we mentioned, not all components are running at full power simultaneously. Nobody is saying that your CPU is running max when your GPU is running max. Usually it hands off a workload to the GPU and then sits there quietly doing nothing while the GPU is running max. Also, components don't necessarily run at their rated maximum power depending on the software. That's a big thing. Like my 1080 Ti is rated at 250 watts, but generally when I'm rendering with some software, it's maybe 150 or maybe 200. So it depends a lot on the software, and people don't even think about that, but that's a big issue. So let's now look at what really does a power supply do, all right? And we're going to have to mention a couple more concepts in electricity that you're going to need to be familiar with, and one is alternating versus direct current and voltage. What does that mean? Well, when you plug into the wall, or when you bring wires in from the utility to your circuit breaker panel, the voltage and current that are coming in look like this. It's not a flat value of 120 volts, it's varying. It's kind of like, if we go back to our garden hose, if the water coming out was pulsing, it was going maximum and then it stopped, and it pulsed out and then it stopped, right? It's pulsing, and it's called alternating current and voltage, versus direct, which is kind of a continuous flat value. Now, there's a reason why it comes from the utility that way, and it's a fairly complex discussion of this type of varying current and voltage allows the utility to do transmitting current and voltage power over long distances to your house without losing a lot of power needlessly. So that's a whole different issue, but this is a lot more efficient to do it this way rather than just send direct current. So one of the main reasons why you have a power supply is to convert this varying current and voltage to something that's flat and continuous. And the reason for that is because electronics need flat, continuous voltage to do their thing. All the integrated circuits and the CPUs and the memory want a fixed value of voltage in order to be able to do their stuff. So one of the main requirements of a power supply is to convert this varying electricity from something that's called a sine wave into something that's flat, okay? And the voltage coming from the utility, we mentioned, is like 120 volts alternating. Your computer doesn't want 120 volts. If you applied 120 volts to your motherboard, it would blow up, right? Your components want something like 3 volts DC direct current, like this, or 5 volts or 12 volts. In that range. So it has to convert from the varying sine wave to the flat values, and it also has to bring this 120 volts down to 3 or 5 or 12 volts. Okay? So the power supply primary roles are convert from this AC, alternating current, to DC, and then get that value, the magnitude of 120 volts, down to around 3 or 5 or 12 volts. But the third role, and very, very important that people tend to not realize, is it has a third role, and that is to filter and protect itself and also whatever it is supplying. So it has to, when you get your electrical source from the utility, it may not be a clean wave. It may be, it may instantly jump high, and that can be damaging to your components, or it might go low, and it might not be really clean because of stuff. There's generally thousands of miles of electrical wires before it gets to your house, and stuff can happen. So this can be not real clean, so the power supply has to get rid of some of that stuff as much as it can, and it does that by filtering to try and smooth this out so you don't get these high peaks. And also it has to protect your computer and also itself. And it's kind of like the circuit breaker on your breaker panel at your house. One of its roles is to measure the current coming from your computer, and if it gets above a certain value, it opens up a circuit breaker or fuse and protects your computer, right? So it does some filtering and protecting to make sure your computer doesn't get damaged, right? So what am I talking about? Stuff it has to filter and protect. Well, here's an example. You've got your house all going fine. Suddenly you get a storm and you get lightning, which is very, 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 very high voltage, connects to your electrical wires, and it could send some extremely high voltages along the wires. Now, the good thing is the utilities have equipment there designed to cut that down to very low values so it doesn't affect you. However, nothing's perfect and you may get high voltages. So you've generally got on all of your components, especially your electronic components, something that will, if the voltage coming in goes way over 120, it will clamp that down to 120 or something like that, again, to protect your computer and your power supply and your components. So you need to protect against that, and sometimes it's just other types of stuff that aren't as bad. You need to filter it out, but filtering and protection are a very important component of what a power supply does, and people tend to gloss over that and not really understand it, and they think, if something goes wrong, everything's going to blow up. No, engineers design these power supplies so that doesn't happen. So briefly, in their role of converting from this sine wave to the DC, they have to filter. You might get nasty looking voltage that's not nice and smooth, and you might have to filter it. But the other thing they do to convert it to DC is one of their big jobs is called rectification. And rectification is trying to make it look more DC. And the way they do that is they take the negative pulse of this, what's called a sine wave, and they flip it. And there's a lot of high power components in your power supply whose job is to flip this negative part so it looks like this. And you can see this dashed line. That's the flipped wave. And you can see it's getting more and more to look like a DC direct value. And then what they have to do is they have some filtering that kind of smooths this out. So there's a filtering component, there's a smoothing component, and at the end of the day, if you do this right, you can get really close to something that looks like this. In the real world, in components, they generally use stuff called integrated circuits with pulse width modulation. I think I did a video a while ago talking about solar inverters and how they use pulse width modulation to do AC to DC conversion and vice versa. But anyway, the end result is that they're trying to convert this into something like this, all right? So there's one aspect of power supply protection that people don't seem to realize, and it's a really big deal. And it reflects the fact that engineers design these components so that stuff doesn't blow up, right? That's why we have engineers to design this stuff so that bad things don't happen. Now, of course, if you buy a piece of junk power supply that was thrown together and it has nothing in it, yeah, you're going to have problems, but that's up to you. You know, if you're willing to spend money on a decent name brand power supply, you'll be okay for the most part. And the reason is because there's stuff like this, which is called the ATX specification. Now, you may have seen when you bought a power supply, it's an ATX or a motherboard, ATX. What does that mean? Well, many years ago, Intel, I believe, yeah, it was Intel, generated a specification that attempted to make minimum design requirements for computer stuff, including power supplies and motherboard configurations and dimensions, and tried to standardize to make sure everybody's up to kind of a minimum level and like a standard equipment design that people can use. And that's really good for users because it says, okay, well, we can be kind of sure that when these companies design these power supplies and motherboards and everything, they come up to this minimum specification. In this case, it's called the ATX, which is very common today. And ATX requires that if you're going to sell something under the ATX specification, you've got some internal protective elements like we talked about. Specifically, you need overcurrent protection, like that 15 amp circuit breaker on your house. It checks how much flow. If something's going bad in your computer or with your power supply, it senses that and it shuts off the power, and your power shuts off and you blow a fuse or you open a breaker. It's also got short circuit protection, which is a very high overcurrent caused by a short circuit, which is, you know, it's not something with, well, we won't get into what it is, but it's basically when very high currents flow for a short amount of time, it opens it up. And then there's overvoltage protection. We talked about, you know, if a surge comes in, a high voltage comes in from a lightning strike or something, and it's not fixed by the utility, it should have overvoltage protection to clamp that voltage so it doesn't get too high, again, protecting whatever's connected to your power supply. So as a minimum, if you buy a well-designed ATX power supply, it has protection in it. And if you look at the specifications or the diagrams for your power supply, if you can find it, you will see integrated circuits, and I can show you in mine, it's got an integrated circuit whose whole job is to provide overcurrent, short circuit, and overvoltage protection, and it does that hopefully very well so that you don't have to worry about stuff. Now, that doesn't say that even higher end units don't have even more protection, because they do. Higher end units can have much more protection, such as over power, over temperature. If things start to heat up, it will shut it down or it will throttle. So there's a lot of stuff going on that people don't seem to understand, and they get all this paranoia about power supplies that, they're going to blow up, they're going to blow up your computer. Well, in fact, the power supply is designed to help your computer and protect it. So, again, this doesn't apply 100% of the time to everybody everywhere. Stuff can fail. It's equipment and it's software and it can fail. But just you can, take some solace in realizing that it's not always the case. And in fact, in most cases, you can pretty much rely on, if something went wrong with your computer, maybe you were the one that caused it. And maybe, the rest of the components are designed to protect against stuff going wrong. So the next thing I want to talk about is power supply efficiency. And there's a wonderful myth that keeps getting amplified and repeated on the internet about power supply efficiency. Now, what does that mean? Well, over here on the right, I am showing some major components in your computer and how much power they might be taking at any point in time. So your GPU, maybe it's rendering away and it's or doing a video game and it's requiring 200 watts. And your CPU at the same time is requiring 100 watts to do whatever it's doing. And your motherboard components are requiring 100 watts. All right? So total, your computer at any point in time, add it all up, you're requiring 400 watts. So it's asking for 400 watts from your power supply, whose job is to supply it power. Well, the power supply itself, just like, for example, your motherboard, in order to power the components that do all the protective elements and the filtering and all that, it takes power to run those, just like your GPU and your CPU and your motherboard need power. The internals of the power supply require some power. So you might be asking for 400 watts, but your power supply is going to take another 100 watts maybe in order to do its work. So 400 plus 100 means you're going to be asking from the utility 500 watts, right? So you're going to be taking 500 watts from the utility, but your computer only needs, technically, these components only need 400 watts. In fact, your entire computer needs 500 watts, but some reason people don't like the fact that your power supply requires power. So what they do is they say, okay, this power supply is only 80% efficient, requiring 500 for a 400 watt computer requirement. So maybe you can get a higher efficiency power supply that needs less power. So let's go through, and this is going to be a little math, so hang in there. But we're going to show what it really means in terms of real numbers. So if you look on the internet and you look, I'm going to talk about the US, the typical cost to a user for electricity, for example, to use 1,000 watts for 1 hour, the average throughout the US is it costs you 13 cents to use 1,000 watts of power for 1 hour. So if you're running your microwave, which is say 1,200 watts, for an hour, it might cost you 15 or 20 cents, something like that, right? So that gives you an idea. To use 1,000 watts for 1 hour costs 13 cents. So let's say I've got a 500 watt power supply and I'm running it continuously at 500 watts for 24 hours. Now, most people aren't going to do that. Keep that in mind. But let's say worst case, 500 watts continuously for 24 hours, like you're playing a game for 24 hours or you're rendering something and you've got multiple GPUs or whatever. Again, very unlikely, but let's say 500 watts, 24 hours, that will cost you 24 hours times 13 cents an hour times only 500 watts, not 1,000, means $1.56 per day to run 500 watts per day continuously. Now, if I do that again the next day and the next day and the next day, I do it continuously every day, 365 days, an entire year, that running that computer at 500 watts continuously will cost $570 per year to run the computer. This has nothing to do with efficiency. This just has to do with the cost to run 500 watts continuously for a year. is $570. Now, let's get back to the real world and talk about actual expected usage. Generally, your computer is going to idle, we said, at maybe 50 to 100 watts. And I showed mine normally idles, even when I'm recording a video, at about 80 watts, 80 or 90 watts when your computer is powered on. Now, your microwave, as we said, is 1,000, maybe 1,500 watts. Your toaster oven is 1,000, 2,000 watts. A light bulb might be 50 to 100 watts. Air conditioner might be 1,000 to 4,000 watts, right? So in the scheme of things, your 500 watts is pretty low compared to, 4 or 5 light bulbs is about the same as your computer, and it's much less than your microwave, toaster oven, and air conditioner. So if I run my measly computer at 100 watts for 1 hour, 13 cents an hour, that's going to cost me 1.3 cents. Okay, and again, that's about the same as a light bulb. So you run a 100-watt light bulb for an hour, it costs you 1.3 cents, just so you know. But your measly computer is no different from a light bulb, maybe less. So if I run that computer 100 watts, 24 hours a day, 365 days a year, at 100 watts, it costs me $113 per year to run my computer or to run a 100-watt light bulb, right? So that gives you an idea of what numbers we're talking about just to run your equipment. Now, let's talk about efficiency and the efficiency myth, all right? So let's say if you're using 400 watts, which is a lot, maximum, for 8 hours a day. So let's say you're sitting there doing renders for 8 hours a day, 3D renders, or you're doing some high-powered GPU video games continuously 8 hours a day. If you have an 80% efficiency power supply, which means you're taking 500 watts from the utility rather than the 400 watts the rest of your computer needs, and if it's 90% efficiency, you're only taking 445, so an additional 45 watts from the utility. And here we take an additional 100 watts. So the difference between these two efficiencies is 55 watts. Between a high 90% efficiency and a lower 80% efficiency, the difference in requirement or over usage from the utility is 55 watts. That is 0.055 kilowatts, all right? For 8 hours a day, that's 0.44 kilowatt hours, all right? So at 13 cents a kilowatt hour, which is the typical rate, that's 5.7 cents a day additional cost if you're going to use a 80% efficiency rather than a 90% efficiency. 5.7 cents a day. If you do that 8 hours a day for 365 days, the total cost difference for the 80% efficiency rather than 90% efficiency is $20 per year, okay? So keep in mind, we're talking about running at 400 watts, 8 hours a day, 365 days a year, which few, if anybody, is going to do. And the difference in efficiency cost is $20 a year, all right? That's the same as leaving a single light bulb on or maybe 2 light bulbs in the house. Because again, it's a 55 watt difference, which is a light bulb. Or maybe only half a light bulb if you're using 100 watt light bulbs. So the big question, let's get real here. Do you really worry about turning off light bulbs so that you don't waste, the wattage? Do you run around, do you really run your computer max 8 hours every day for an entire year? So, to be realistic, we're talking about maybe at worst $10 or $20 a year difference for the difference in efficiency of power supply. And that's, no different from a light bulb. So if you're going to be consistent, you better go running around turning off the light bulbs, or you should be turning off your air conditioner, which is really using, 1,200 watts. If you really want to save power, turn off your air conditioner for an hour where you normally have it on. So, let's just give you a general perspective about what's the real cost. And, let's come into the real world and use real world numbers. So if you don't believe this, and this is something people never do, and I never understood why people don't do this. you can spend $20 or $30 and get a watt-hour meter and place that between your outlet that you plug your computer in and your computer wire. And you can see here I've got this black wire coming from my computer power supply, and I've got this little module I plugged in, and this wire comes around and feeds this watt meter, and I've got the power strip getting power from the utility, from the wall outlet. So it comes from the wall outlet through this little module and then into my computer. And this module is measuring how many watts are being consumed in total by my computer. The GPU, the CPU, the motherboard, everything. This is a total reading of watts. And you can see 79.9 watts. And this is what I normally see when I'm doing normal work on my computer, even right now when I'm, doing a video. Okay? So, if you want to erase all doubt, spend $20 or $30 and get this. It will give you the actual total wattage being consumed by your computer at the wall outlet, the entire computer usage. There's another one which is a little bit nicer I don't have, called a kilowatt, and it gives voltage, amps, watts, and frequency. All right? So, measure it yourself. Don't take people's word for it. If you really think you're using 800 watts, get one of these and remove all doubt, okay? It will help to remove a lot of myths if people actually see what they're using. So, in the end, I've got maybe 5 myths that I'm hoping we've given some data that will help debunk the myths. And here's the myths I'm hoping to address. People will say, my power supply failed and destroyed my computer. Whenever I hear that, or anything like that, my immediate response is you probably destroyed your computer, or you bought a power supply that's a complete piece of junk, right? We showed that there are protective elements in your power supply, protective elements at your breaker panel, protective elements even at the utility that are designed to make sure your equipment doesn't get destroyed. Again, that doesn't mean 100% that nothing's going to happen, but I'm just saying there's a lot of stuff there you should know about, and don't immediately assume that your power supply, has no control whatsoever and the engineers didn't design anything, it just exploded for no reason. That's just absolute nonsense, right? They design stuff into it, they're required to design stuff into it, and if you get a good power supply, you should be pretty much in good shape. Myth number 2. People are convinced, and I've never understood this, a lot of tech people will say, I need a 1200 watt power supply or something equally unreasonable for my computer because it's a beast. They think, okay, I'm buying the best computer, I'm buying GPUs, and I'm buying big CPUs, and I'm buying a great case, and I'm using LCD lighting, and it's going to need water cooling and blah, blah, blah. This is nonsense, okay? Maybe if you are really overclocking and you've got multiple, you've got server farms and you're using a single power supply or something, nobody needs 1200 watts, especially not the regular user. If you are a corporate or you're a company or you're running a company that does render farms or something, you might need that. Certainly if you're running, some of the farms of multiple GPUs, yeah, but that's not normal people. The vast majority of users need 650 watts or less. If you don't believe that, again, buy a 25 watt meter and actually measure your power usage to remove all doubt, okay? Now, another thing I've heard that I just don't quite understand is people think if I buy and install a 1200 watt power supply, it will overload my house wiring. Again, that's pretty much nonsense for a couple of reasons. First of all, like we said, you don't have nearly the amount of power components that will require anywhere near 1200 watts, right? Again, you may be an exception, but I strongly doubt it. Again, measure it if you don't believe it. Even if you do, it's no different from buying a 1200 watt microwave oven or window air conditioner and plugging those in, right? So, make sure that the circuit you're on, already have a 1200 watt air conditioner and it's a 15 amp circuit, then obviously, use your head and don't overload it that way. But, the chances are you don't need 1200 watts, all right? The next myth is I need to buy a high efficiency power supply or my electric bills will go through the roof. Again, utter nonsense for most people. Again, we said the difference between the 70 to 90% efficiency power supply is probably only a few dollars per year in electricity bills, all right? Again, you may be an exception, but at least use these numbers to as a springboard to determine your own numbers. And honestly, if it really mattered to you, this few dollars of difference in your electrical bills, you'd be running around all the time shutting off unused light bulbs and not running your air conditioner so long, right? If you really cared about it. So, it's one thing to use numbers or use data to justify stuff, but at least do it, using the right numbers and being rational, right? And the last one, when all else fails, people fall back to the unprovable nonsense of you need a monster power supply to future-proof your computer, right? If nothing else works to justify your point of, I want a big power supply because I want it, they say, oh, I'm future-proofing. Again, that is utter nonsense. Most people replace their PCs after 3 to 5 years or lose interest in the stuff that they're doing that requires a lot of power, right? Are people going to, in 3 to 5 years, are going to be playing the same video games? Are you going to be doing your 3D rendering, or are you going to lose interest in a year and go do something else? And as we mentioned, few people actually need more than 650 watts ever, right? So, what are you future-proofing? If you're running 300 watts on a 650 watt power supply right now, do you need a bigger power supply in the future? You'll be lucky if you get up to 400 or 500. And also, if you're not aware, if you look at some of the Intel and AMD data on their design trends with electronics like CPUs, and the current trend in PC electronics is to vastly improve the power efficiencies of electronics components with each new release, which means they are trying to cut down the power usage while increasing the functionality, because everybody's going to smaller and smaller components and they want more and more functionality with smaller and smaller components, and the only way to do that is cut down the power requirements. So you don't need these big cooling solutions on smartphones and tablets and stuff like that, because that's where everybody's going. So you need a 16 core CPU that runs with only 10 watts. That's the goal, to reduce power requirements so you can put more components in smaller spaces. So again, if you look at some of the new components coming out, that it's surprising how the power requirements are dropping. Some of the newer CPUs are doing a lot more with less power. So again, you can fall back and say, I need future proofing just to prove that, the power supply you bought was really necessary, when in fact it was just, you like big power supplies because it makes you feel good. So again, these are some of the myths. I'm hoping that at least people will use the data that I'm providing and use that as a springboard to do your own research and figure out exactly what do you need, and are some of these things really legit, or is it just people talking from lack of knowledge? So hope this stuff helps you, and I hope you take care and have a really good day. Thanks.